the preceding, that shows us that the potential energy relative to the equilibrium position is 1/2 kx squared. That is, as we saw, the potential energy change as you stretch from the x equals 0 position to position x is 1/2 kx squared. So if you set the potential energy equal to 0 at the x equals 0 or equilibrium position, then at position x, the potential energy will be 1/2 kx squared. So we have this kind of triangular relationship, one of many triangular relationships. We have the force constant, we have x, we have the potential energy. If we know two of these, we can find the third. If we know k and x, then the potential energy is 1/2 kx squared. If we happen to know k and potential energy, well, we'd be able to set 1/2 kx squared equal to the potential energy and solve for x. So, and similarly, if we knew potential energy and position, we'd be able to solve for k. So there's a very informative relationship right there. Okay, now we have the problem says a mass is displaced 7 centimeters, and this is on the spring of the first problem, or the system of the first problem, where the force constant was 8 newtons per meter. That is the spring in which the 400-gram object oscillated with an angular frequency of 4 pi over 3 radians per second. First problem. So using that again, getting a little more information about that system. We just place that system 7 centimeters from equilibrium, release it. We'll get an oscillation with an amplitude of 7 centimeters. Okay, so we say A equals 7 centimeters. A stands for amplitude. Amplitude is the maximum distance the oscillator goes from equilibrium. So if the oscillator is going this way, equilibrium's halfway between here and here. So we're oscillating here to here, and halfway between us here. This is the equilibrium position. The amplitude is the distance from the equilibrium to this extreme, or from the equilibrium to this extreme. I'm not sure my fingers are clear there, but you get the idea. Okay, now, if the amplitude is 7 centimeters, we say the total energy is the potential energy that you have at that position. Why do we say that's the total energy? Well, the oscillator goes out to the extreme position and comes to rest for an instant before it comes back. Passes through equilibrium, and its maximum velocity occurs at equilibrium, as we'll see, and then it slows down to the next, to the maximum distance on the other side. Velocity is 0. Okay, well, here we are at a maximum distance, at distance A. The potential energy is 1/2 Ka squared. No argument with that. Just plug K x equals A in here, and you get 1/2 Ka squared. There's your potential energy. How much kinetic energy do we have at this position? Well, we're stopped. We don't have any kinetic energy at this position. So that is the total energy. That is the total mechanical energy, if you want to be a little more precise about it. The sum of the potential and kinetic energies. Okay, that's the sum of the potential and kinetic energies at any point of the oscillation. Okay, so I can say that this equals 1/2 Kx squared plus 1/2 mv squared at any point. Why is that? Well, the force is conservative. So the force on the way back exerts exactly the accelerating force that it did on the way out, except that now the accelerating force is in the direction of the motion. So we speed up. The accelerating force is opposite the direction of motion as we went back this way from equilibrium. When we move away from equilibrium, the force is back toward equilibrium, so we're moving in the direction opposite the net force. The net force is therefore going to slow us down. Okay, well, by the conservative nature of the force, whatever potential energy gets lost is gained by kinetic energy, by the conservative nature of the net force. Okay, if there were frictional forces, as there are in reality for most oscillators, then this won't quite be true. You'll be losing energy to friction, to other to other forces and other interactions. The ideal case, though, total energy is 1/2 kA squared. You set the thing in motion, it continues going forever until something brings it to rest, until you decide to stop it, let's say. And in that case, the sum of the potential and kinetic energies is at every point the same, and that's equal to the total energy, which is the potential energy at maximum distance from equilibrium. Okay. If the maximum displacement is 7 centimeters, your potential energy at that point is 1/2 kx squared, and we work that out, and we get 0.02 joules, ballpark. I think it's a little less than that if you actually do the calculation. I think it's 0.0196 joules, but you can check that out. That's the total energy of your oscillation. Now, we want to know how fast this pendulum is moving, or this object is moving when x equals 3 centimeters, at the 3 centimeter position. Well, at 3 centimeters, the potential energy is 1/2 kx squared. We calculate that for the 0.03 meter or 3 centimeter position. We get 0.0036 joules. Okay? Now, potential energy at maximum displacement is 0.02 joules. You get to the 0.03 meter displacement, and potential energy is down to 0.0036 joules. So that's a loss of 0.0164 joules of potential energy. There are no dissipative, no non-conservative forces, so that the loss of potential energy is accompanied by an equal and opposite gain in potential energy, in kinetic energy. A loss of potential energy is equal to a gain in kinetic energy, the gain being of the same magnitude as the loss. Okay, so here's our change in potential energy. So our change in kinetic energy has to be plus 0.00164 joules. And notice I'm being a little sloppy with significant figures here. As usual, we don't worry too much about that because it can distract. But of course, when you're actually doing a problem after you get onto this, you need to get your significant figures right. Okay, we have a change in kinetic energy of, again, 0.00. It's not 0.00, it's 0.0164 joules. Let me fix that. Okay, again, from maximum displacement to the 3 centimeter position, we've lost 0.0164 joules of potential energy, so we've gained 0.0164 joules of kinetic energy. Now, how much kinetic energy do we therefore have at the 3 centimeter position? Well, at the maximum displacement, our potential energy was, of course, 0.02 joules. We lost 0.164 joules. At the maximum displacement, our kinetic energy was 0. So we've gained the 0.0164 joules of kinetic energy, starting with 0, meaning that we now have kinetic energy of 0.0164 joules. So the kinetic energy at the 3 centimeter position is the change in kinetic energy. And now we can set 1/2 mv squared equal to the kinetic energy. Remember, our mass was 0.4 kilograms. Solving 1/2 mv squared equals kinetic energy for v, we get v equals plus or minus the square root of 2 times the kinetic energy over the mass. We just plug in our kinetic energy, we do the arithmetic, and we get plus or minus 0.3 meters per second. Now it's actually more like 0.28. But in keeping with the spirit of very approximate calculations that you should therefore go and refine, just rounded that up to 3 meters per second as a guidepost. So, or as a guideline. So we've reasoned this out. We can diagram what we've done. We basically have the information we get from 2 triangles. One, Ka in total energy. Now, that's very much like Kx in potential energy. but A is the maximum displacement, the displacement at which there's no kinetic energy. So if we use A instead of X, we get the total energy of the oscillator. And then, of course, we have the same triangular relationship we had here, and that gives us our potential energy. So here's our total energy, here's our potential energy at position X, and now we can infer the kinetic energy. We subtract the potential energy at this position from the total energy, and that gives us our kinetic energy. And now we're back on very familiar ground because we know how kinetic energy and mass and velocity are related. I'll re-emphasize the critical importance of the relationship between omega, k, and m with 4 exclamation points. It's something I warn people again and again and again that is central, that you really need to do much of anything with simple harmonic motion in this class, and yet we get to the exam and almost nobody seems to have believed me. So believe me this time, please.